In this presentation, I'll be explaining single phase half wave control rectifiers. Now let us see the types of rectifiers. In this slide, I'll be explaining single phase. Next slide, I'll be explaining three phase. Now coming to the type of rectifiers, as I know, single phase as well as three phase rectifiers are there. In single phase itself, control rectifier is there. Sorry, uncontrolled rectifier is there and control rectifier is there. Uncontrolled rectifier means that is only the uncontrolled switching element, that is diode is using in uncontrolled rectifier. And in control rectifier, instead of diode, we will be using control switch like SCR, silicon control rectifier is using. Now coming to the uncontrolled rectifier, again that is classified into half wave as well as full wave. Again, full wave, there are two types, split supply type as well as bridge type. Therefore, here, if you consider the first bridge type, it is a single phase uncontrolled full wave bridge rectifier, uncontrolled rectifier. That is shown here. This is a bridge rectifier. It's an uncontrolled type, and it is here input supply, single phase supply is given. There are four diodes we are using. That is D1, D2, D3, D4. Therefore, four diodes are using as a bridge, and here the single phase AC supply is there. And here you'll be getting the rectified output across the load. Second type is called split supply type. Instead of using two supplies are coming here. Therefore, at the primaries there are only single AC supplies there, but that is split into two. There are 180 degree. That the voltage at this point and this at this point they are 180 degree out of phase. And rather than using four diodes, in this case we are using only two diodes. Therefore, here this topology of is called full wave uncontrolled rectifier, that is using the split supply. That is the second one. That is the bridge single phase uncontrolled full wave using split supply. The third one is called the half wave, that is single phase uncontrolled half wave type. That is shown here. This is also an uncontrolled rectifier. Only one half it can control. For example, when the diode is getting forward bias during the positive half cycle, then you will be getting output voltage. But during the negative half cycle, this is reverse bias and you won't get any output. For only one half it is controlled. That is why it is called half wave control, uncontrolled. Sorry, even it cannot control as such. Only it can conduct only the half wave. That output rectified output will be getting here. Therefore, we are using a diode in this case also. Therefore, these three are uncontrolled rectifiers. Now coming to the control rectifier, there are single phase control rectifier. There are half control as well as fully controlled. This is a half control rectifier in which we are using only using SCRs are used. Rather than using a diode, here using an SCR, silicon control rectifier. By controlling the firing angle of this SCR, you can vary the average output voltage across the load. Therefore, this is called a single phase half control rectifier. And the other one here, fully controlled rectifier is shown here, that it can control both half. In this case, this can control only the one half. During the negative half cycle, this is getting reversed by, it cannot be controlled. During the positive half cycle, by controlling the firing angle, you can control the voltage. But in order to control the both half, you have to replace this circuit by a bridge rectifier in which there are four SCRs are using T1, T2, T3, T5. During the positive half cycle, these two T1 and T2 are fired, and during the negative half cycle of the input, T3 and T4 are being controlled, so that both half can be controlled and it can vary the average output voltage of this one. This is the second type of fully controlled single phase, of course, bridge rectifier. Now coming to the rectifier three phase type. Three phase rectifiers also again that can be classified into uncontrolled rectifier and controlled rectifiers. Uncontrolled rectifier, again there are two types, half wave as well as full bridge uncontrolled rectifier. That is shown here. This is an uncontrolled rectifier because we are using diodes here, and this can be controlled. That is three phase uncontrolled rectifier half wave. Only one half it can control because only during a positive half cycle this is getting forward bias. Not even controlled, it's uncontrolled here. Only positive half cycle it can pass through one, you will be getting the output voltage across the load. But during the negative cycle, this is getting reverse bias. There won't be zero output voltage. Therefore, it's an uncontrolled rectifier which can control only one half. That's called half wave uncontrolled rectifier. Now, in the case of a bridge rectifier, uncontrolled bridge rectifier, there are three legs. In each leg, there are two switches like, of course, D1, D3, D5, D2, D4, D6, like that. This is a bridge rectifier. This is also an uncontrolled rectifier. You cannot control the voltage magnitude here, and here you'll be getting a DC output voltage across the load. This is an uncontrolled rectifier. Here we are using again diodes are being used. Now, if you replace these diodes by SCRs, then you can have a control rectifier. Now, coming to the control rectifier, half control rectifier and fully control rectifier. Now, this circuit is a three-phase half-wave control rectifier. Therefore, three-phase supply is three-phase signal is here, or that three-phase, it's a half control rectifier. Only one half it can control, because during the positive half cycle it is getting forward bias, and during the negative half cycle it is getting reverse bias. That's called, it cannot conduct. Therefore, one half it can control. That is called half wave control rectifier. And this is a full wave control rectifier, three-phase fully controlled bridge rectifier, in which here, similar to this one, only thing is that rather than using a diode, that is, we are using SCS are used. That is, the three-phase, R phase, Y phase, and B phase. In each phase or in each leg, there are two switches, top switch and bottom switch. In this positive type, and this is, of course, the positive, this will be conducting during the positive voltage of this one, and during the negative voltage of this input, the lower switches can conduct. Therefore, of course, by controlling the firing angle of this thyristor, the average voltage across the load can be controlled. Therefore, this is a three-phase, fully controlled bridge rectifier for this one. Now, coming to the control rectifier, a diode rectifier provides a fixed output voltage. By using a diode, you cannot control the output voltage. So that gives a fixed output voltage. To obtain a controlled or variable output voltage, these diodes are being replaced by thyristors or other power electronic switches like MOSFET, etc. IGBT, MOSFET, etc. Controlled switches can be used so that you can vary the output voltage. The output voltage is varied by controlling the firing angle of the thyristor or other power electronic switches. By controlling the firing angle of the SCRs, we can vary the output voltage. Now, SCR is turned on by applying a gate pulse, and it can be turned off either by natural commutation, that's called the line commutation, or by force commutation. Therefore, that it can be turned on if the current is going above the latching current, that gets turned on, and if it is going less than the halting current, that gets turned off. Therefore, SCR can be turned on by applying the gate pulse, and it can be turned off by natural or line commutation, or it can be force commutation. For this is the control rectifiers, can produce a control rectifiers. Now, coming to the single phase half wave control rectifier with R load, that is single phase half. This is a single phase half wave control rectifier with R load here. Assumption is that source voltage is purely sinusoidal. This input voltage is a purely sinusoidal. Source voltage is a purely sinusoidal. Second assumption is that devices are ideal. Ideal in the sense, when it is conducting, the voltage drop across the device is equal to 0. It's ideal case. And when it is turned off, the voltage, the leakage current equal to 0. For this ideal case switch characteristics, for devices are ideal, we are considering that one. And source inductance is negligible. The inductance at the source side is negligible. For third assumptions. Now, coming to that one, during the this is the input signal. And during the positive half cycle of the input signal, this SCR is getting forward biased. SCR is getting forward biased during the positive half cycle of the input signal. And during, that is from 0 to pi, this is getting forward biased. And from pi to 2 pi radians of the input cycle, here this is getting reverse bias. For again, that is repeating. Again, 2 pi to 3 pi is forward bias. Therefore, when the device is getting forward bias, you can give the firing pulse, and that can make to conduct. For example, here at firing angle alpha, you are giving a switching pulse. That here a switching gate pulse is given at a firing angle alpha here. Once it is getting turned on, it is just like a switch. It is getting turned on. The output voltage is same as the input voltage. Therefore, here at the firing angle alpha, this device T is or SCR is getting turned on. Then output voltage is same as the input voltage, or this voltage is same as the input voltage. And at pi radians here, the voltage is getting reduced to 0. And as the voltage gets reduced to 0, here the current through the device gets 0, and same, since the current is going less than the holding current, the device gets turned off. Therefore, at this instant, of course, the device is getting turned off, and here again the voltage is getting 0 voltage. And during the negative half cycle of the input, this SCR is reverse bias. That is why, since it is just like an open, it's a switch, it's an open switch here, then the output voltage equal to 0. Therefore, from pi to 2 pi, the SCR is not conducting. Therefore, the output voltage equal to 0. Then again, at the 2 pi plus alpha, at that instant, again this SCR is getting turned on. Then once it is during the pi 2 pi, after 2 pi to 3 pi, again that's forward bias case, and 2 pi plus alpha, that device is getting turned on by applying the firing switching pulse. Then again the output voltage is same as the input voltage. Therefore, this is a waveform of the output voltage. And if you calculate the current, output current as such, output current is given by, see, at firing angle alpha, if you see that one, at firing angle alpha, the input voltage is, or input voltage equal to Vm sin alpha. Therefore, at that instant, the output voltage is same as the input voltage when it is getting conducting. Therefore, the output voltage is Vm sin alpha at firing angle alpha. This is the input voltage, and which is same as the output voltage at alpha. And at the same firing angle here, since the device starts conduct, or the SCR is conducting, it's just like a closed switch. Therefore, the output voltage is same as the input voltage. Therefore, the voltage at the output equal to Vm sin alpha. Therefore, the current through this one is equal to Vm sin alpha divided by R, or Vm by R into sin alpha, which is equal to Im sin alpha. Therefore, this is the Im sin alpha, which is the current through the resistance at alpha. Therefore, this is the again Vm by R into sin alpha. Vm by R into sin omega t is this current. Therefore, here this will be in phase to this voltage. So the output current will be in phase to the of course the output voltage. Therefore, this is the load current waveform, and this is the output voltage waveform. And in order to calculate the voltage across the switch, across the device, which is equal to, you can apply the Kirchhoff's voltage law here. The input voltage is equal to the sum of the voltage across the device switch and the voltage across the load. Therefore, then the voltage across the device switch equal to this voltage minus this voltage, input voltage minus the load voltage. Therefore, this is the input voltage and this is the load voltage. If you subtract the load voltage from this one, then you will be getting what is the voltage across the switch. Therefore, the voltage across the switch is this one. You can see that one. That is when the device is not conducting, the voltage across the switch is same as the input voltage. You can see that one. Here, this is the input volt. I mean the input voltage when the switch is not conducting. Therefore, this is the voltage across the switch here, and this is the current through the load, and this is the voltage across the load, and this is the input voltage. Again, as I explained in the previous slide here, single phase half wave control rectifier, same as this one. A single phase AC input is there, and here the resistive load is there. This is a thyristor as it is getting fired at this instant at Vm sin, at that alpha. The corresponding is when it is getting fired, the voltage output voltage is same as the input voltage at alpha, which is equal to Vm sin alpha, and current is given by that divided by Vm sin alpha divided by R. Therefore, that is the current at this instant, and therefore the current waveform, and sorry, this is the current Im sin alpha. Therefore, this is the current through the resistance, and this is the voltage across the output, the resistance or output voltage as such. And here this is the voltage across the device, which is nothing but voltage at the input voltage minus the load voltage is the voltage across the device. Therefore, this is the voltage across the device, and the maximum voltage, you can see that the maximum voltage across the device is given by, of course, the magnitude equal to minus Vm, actually is magnitude equal to Vm. Therefore, the reverse voltage, maximum reverse voltage that is across the device is equal to Vm in this case. Now, continuing the single phase half wave control rectifier resistive load, we have to find out in this one what is the average value of the output voltage and what is the RMS value of the output voltage. For the output voltage is this one. This is the output voltage waveform. Therefore, this is the input voltage. Firing pulse is this one. This is the output voltage. You have to find out what is the average value of the output voltage, and similarly what is the RMS value of the output voltage. Let us see first one. Instantaneous value of the voltage equal to Vm sin omega t. This is the Vm sin omega t, and average value of the output voltage is given by, you we have to take average values given by 1 by 2 pi integral alpha to pi, because this output voltage is from alpha to pi. From pi to 2 pi it is 0. That is why we have to integrate this voltage from alpha to pi, and that is to be distributed over 2 pi radians. Therefore, 1 by 2 pi integral alpha to pi Vm sin omega t d omega t. That is the average value of this voltage, and which is equal to Vm by 2 pi minus cos omega t, that is alpha to pi range, or Vm by 2 pi into 1 plus cos alpha. Therefore, the average value of the output voltage across the resistance, that is given by Vm by 2 pi into 1 plus cos alpha, where alpha is the firing angle of the thyristor. And the average value of the output current is given by average value of the output voltage divided by the resistance, or it is equal to VDC divided by R, which is equal to the average value of the output current. And now coming to the RMS value of the output voltage. What is the RMS value of this voltage? Root mean square value of this voltage. In order to find out the RMS value of this output voltage, it is equal to root of 1 by 2 pi integral alpha to pi square of this value. What is the square of the value? Vm square sin square omega t d omega t. And that is to be integrated from alpha to pi. Alpha to pi. Therefore, root mean square. This is the square. We are taking the mean and then take the root. Let's call root mean square value. Therefore, square root of 1 by 2 pi alpha to pi Vm square sin square omega t d omega t. Now expanding that one, it is equal to root of 1 by 2 pi alpha to pi Vm square, that is sin square omega t, can be written as 1 minus cos 2 omega t divided by 2. Or cos 2 omega t equal to sin square omega t. That is why 1 minus cos 2 omega t divided by 2 d omega t. Expanding that one, Vm by 2 into square root of Vm by, it is equal to Vm we are taking outside, Vm by 2, there are two 2's are, Vm by 2 into root of 1 pi into omega t minus sin 2 omega t divided by 2. Integrating this one, cos 2 omega t sin 2 omega t divided by 2. That is range is from alpha to pi. Then substituting the limits here, that's equal to RMS value equal to Vm by 2 into root of 1 by pi integral. Here substituting these limits here, pi minus alpha plus sin 2 alpha divided by 2. Therefore, this is the equation for the RMS value of the output voltage. This is the output voltage waveform, and the RMS value of the output voltage is given by Vm by 2 into root of 1 by pi minus alpha plus sin 2 alpha divided by 2. And average value already we got it. It is equal to Vm by 2 pi into 1 plus cos alpha, average value of the output voltage. Now, once you get the RMS value as well as average value of this one, you can find out the term what's called the form factor. Form factor is the ratio of the RMS voltage or RMS value divided by the average value. That is Vrms divided by Vdc. That is called the form factor. For example, in this case, for an alpha equal to 30 degree, if you are taking the firing angle equal to 30 degree, and Vdc can be calculated as it is equal to 0.297. From this equation, you can calculate average value of the voltage equal to 0.297 Vm, where Vm is the maximum value of this voltage. If 10 sin omega t, it becomes 0.297 into 10 or 2.97. Similarly, the RMS value of this voltage is given by 0.157 Vm. If again it is equal to 10 sin omega t, it will become 0.157 into 10, or it is equal to 1.57. Therefore, this is the RMS value and this is the average value, and the ratio of the RMS value to the average value we call it as form factor. Now the ripple factor, how much is the ripple content is there, how much is the variable content or ripple content is there, that is measured by the factor we call it as a ripple factor. So actually it is called VRRMS divided by VDC. RMS value of the ripple content divided by the average value. That is called the ripple factor. And the equation is called root of Vrms minus VDC whole square divided by, related to VDC, how much is the ripple content is there. So this is the ripple content, then how much it is related to VDC. Root of Vrms square minus VDC whole square divided by VDC. Or if we again substitute here, reducing this one, we can get Vrms divided by VDC whole square minus 1. Or Vrms by VDC is already we call it flip. This is a form factor. Square root of form factor square minus 1. That is a ripple factor. And output DC power, that is the output DC power is given by VDC into IDC. This average value of the voltage into average value of the current. That product we call the DC output power. And AC output power is given by RMS value of this output voltage into the RMS value of the output current, or VRMS into IRMS. At the output side, we call it as RMS value of the voltage and RMS value of the current, which is equal to the output AC power. Therefore, the output AC power and output DC power equation is there. Then rectification efficiency is given nothing but it is the PDC divided by PAC. What is the output DC power? That divided by output AC power. That is PDC divided by PAC into 100. That is called the rectification efficiency, eta, of the circuit. And one more thing is that transformer utilization factor is there. Transformer utilization factor means that how much is the DC power, PDC, and how much is the AC power at the input side. At the source side, what is the AC power? Source side AC power is given by RMS value of this voltage into RMS value of the source current. That is RMS value of the source voltage Vs and RMS value of the source current equal to Is. In this case, RMS value of the source current is same as the RMS value of the load current. Therefore, this is the transformer utilization factor. And the one more thing is that peak inverse voltage, PIV we call it as. Peak inverse voltage, that is the maximum reverse voltage across the switch. Peak inverse voltage, that is when switch is not conducting or it is a turned off position, what is the voltage coming? Maximum voltage that is across the device, across the switch. You can see that one, it is the maximum voltage is given by this one. Actually minus Vm, magnitude is equal to Vm. Peak inverse voltage is equal to Vm in this case. Now let us see a problem here. If a single phase 230 volt half wave control converter has a purely resistive load of 10 ohm and the delay angle is alpha equal to pi by 2 radians, determine the rectification efficiency, of course the form factor, the ripple factor, transformer utilization factor, and peak inverse voltage of the thyristor. All those parameters to be determined. And of course, the circuit is, as we already seen, it's a single phase AC supply. There is a one SCR silicon control rectifier is there and resistive load is there. By controlling the firing angle alpha, you can control the average DC voltage at the output. And here average output voltage is given by, as we have already seen, it is equal to Vm by 2 pi into 1 plus cos alpha. Vm by 2 pi into 1 plus cos alpha. Alpha is given as pi by 2 radians. Therefore, substituting here, Vm you have to find out first. 230 volt is the RMS value. Here 230 volts is the RMS value. Therefore, the maximum value is given by 230 into root 2. Say sinusoidal input supply. Therefore, 230 into root 2 is the maximum value. That divided by, that is Vm divided by 2 pi into 1 plus cos alpha, cos pi by 2. Then we'll be getting this equal to 51.77 volt. Therefore, VDC is given by average value of the output voltage. This is the output voltage waveform. The average value of the output voltage that is conducting from alpha to pi. Pi to 2 pi it is not conducting. Again 2 pi alpha to up to 3 pi it is conducting. Therefore, in order to find out the average voltage of this one, the equation is that 1 Vm by 2 pi into 1 plus cos alpha. Then we'll be getting 51.77 volts. Then this is the average voltage VDC. Therefore, IDC is given by VDC divided by resistance R. Therefore, 51.77 divided by the resistance is given at 10 ohm, which is equal to 5.177 ampere is the average output current, and the average voltage equal to 51.77. Once you get average output current and average output voltage, then you can calculate what is the DC power output, or PDC you can calculate. Product of that one will give the average out, or PDC, DC output voltage. Now let us see again RMS value of the output voltage. RMS value of RMS value of this voltage can find out, as we already derived equation. Vm by 2 into root of 1 pi into pi minus alpha plus sine 2 alpha divided by 2. So substituting here again, Vm by 2 root 2 into 230 divided by 2 into root of 1 by pi minus alpha is equal to pi by 2 plus sine 2 into alpha, sine 2 pi by 2 divided by 2, or you will be getting 115 volt is the RMS value of the voltage. Therefore, this output voltage RMS value equal to 115 volts and average value equal to 51.77 volts. And IRMS we can calculate. What is the RMS value of the current is given by VRMS divided by R, 115 divided by 10, or it is equal to 11.5 amperes. Now continuing the problem here, The DC power delivered to the load can be, that is DC power delivered to the load is given by what is the average voltage and into what is the average current, that is VDC into IDC, that is equal to 51.77 into 5.177, 268 watts. This is the DC power delivered to the load. Similarly, AC power delivered to load is given by VRMS into IRMS, that is RMS value of this output voltage into the RMS value of this current, which is equal to 115 into 11.5, it is equal to 1322.5 watts. Therefore, this is equal to PDC and this is equal to PAC. Then rectification efficiency, already we have seen the definition. It is the ratio of the DC power delivered to the load divided by the AC power delivered to the load, or PDC divided by PAC into 100. Therefore, it is equal to 268 watts divided by 1322.5 watts into 100, or 20.26% is the rectification efficiency of this particular circuit. And the form factor is equal to, it is equal to the RMS value of the voltage divided by the average value of the voltage, that is 115 divided by 51.77, that is 115 divided by 51.77 equal to 2.22. This is the form factor. And the ripple factor already definition is the RMS value of the ripple content divided by the average value, or VRRMS divided by VDC, or root of VRMS square minus VDC square divided by VDC, or we can calculate it is equal to 1.983. Therefore, this is the ripple factor of the output signal. And transformer utilization factor, TUF, it is the DC power delivered to the load divided by the AC input power. At this, what is the AC input power? From the source side, what is the power? Which is equal to RMS value of this voltage into the RMS value of the source current, which is equal to PDC divided by VS into IS, RMS value of source voltage, RMS value of the source current. But in this case, RMS value of the source current is same as RMS value of the load current. Therefore, which is equal to IS equal to IRMS. Therefore, substituting that one, DC power delivered equal to 268 watts divided by RMS value of the input voltage equal to 230 volt. 230 into, and the current is equal to 11.5. That is the RMS value of this load current, 11.5, or we'll be getting 0.101. Therefore, this is the transformer utilization factor, 0.101. And one more question is that what is the peak inverse voltage of the thyristor? What is the maximum reverse voltage that is coming across the switch, across the thyristor? Maximum reverse voltage, as we have seen, it is equal to the maximum voltage Vm. The reverse voltage minus Vm, actually the magnitude is equal to Vm. Therefore, PIV equal to Vm, which is equal to root into RMS value, that is 230. Root into 230, which is equal to 325.27 watts. Therefore, this is the peak inverse voltage of the PIV of the thyristor or PIV of the switch.